All righty, friends. Good to see you guys. All right, we're going to keep going through this idea of differential equations a little bit. And we're going to start and look at just some more separation of variable type things, some a little bit tougher ones, but still things we can do. So now, before we didn't really have any y's to deal with, but today we're going to actually add some y's. So the goal is to get all the y's on one side and all the x's on the other. So if I were to take this and I cross multiply, so I'm going to cross multiply this real quick, I'd get y dy. And I'd get 4x dx. So we just cross multiply it a little bit. And when we do that, we can integrate both sides. Whoop, there we are. Whoop. And then from there, integrate with respect to whatever variable it is. So we have 1/2 y squared. We don't need to add the plus c because we'll add that on the other side, like we talked about the last couple of days. We have 2x squared, and then we have the plus c. Now the goal here on these differential equations is, if we can, we want to get y by itself. Now you can't always, but if we can, we want to get y by itself. So in order to do that, I'm going to multiply this by 2, and then I'm going to multiply this entire other side by 2. Now, we have y squared on this side. So we have 2 times 2x squared. Well, that'd be 4x squared. Now, I want you to take a look at this here. This is a constant value. So any number. Now, what if I multiply a constant value times 2, I still get a constant value. So we can leave this as plus c. However, it's not the same c as we had before. And when that happens, and you'll see this more tomorrow, but when that happens, we usually just give it a subscript. And we have to give it a subscript because they aren't the same constant number, but it is still a constant number nevertheless. Now, eventually, we'd want to go a little bit further if we could. If we can get y by itself, we'd want to. So something that we could do if we wanted to, and eventually we want to. I won't worry about it today, but I do want you guys to kind of see how we can get y by itself. If we just take a square root of both sides, we end up with plus or minus the square root of 4x squared plus c. Now, where that really comes into play is if I'm trying to solve for a particular solution, if I know an actual value. Now, I don't know that value here, so not needed, but it is something that I could eventually do. Well, friends, why don't you guys go and pause the video, take a second, and see if you can't separate the variables on this other one and see what you can do to solve for y. All right, so let's see here. If I cross multiply this, well, I'm going to move the dx to the right side. So that'll put the dx over here. So if I multiply both sides by dx, I'd move it over there. I really need to get that y to the other side. So the way I do that, friends, I can multiply this side over here by 1 over y. And then I'd multiply this side over here by 1 over y. So if I do the same thing to both sides, I'd end up with 1 over y dy. And on the other side, I'd have 2x dx. Because again, the dx's would cancel out here, and the y's would cancel out here. So we can go ahead now and integrate a little bit. There we are. There we are. And we end up with the natural log of y equals x squared plus c. Now, in order to get y by itself, I'm going to have to change its form. So remember, natural log is the same thing as log base e. So log base e, I can go ahead and swoop and get the y by itself. So if I move the base the other side, it becomes an exponent. So I get e equals x squared plus c. But now I got this absolute value, and absolute value, that could be a positive value, that could be a negative value. What value is it? So if we look at it here and we say, all right, well, I know that this value right here, I know that has to be a positive value. So since that has to be a positive value, friends, I would go ahead and say, all right, well, let's go ahead and let, that means then that that's going to be a positive value. So if I wanted to, then if I know that's positive, and we know that because again, it's absolute value, we can eventually go ahead and get y by itself by calling it positive. So ex squared plus c. And then if we move that c down like that, I can separate this because if I'm adding exponents, I can separate it with multiplication. And then any e raised to the c power is just c. So I end up with c times e to the x squared. Now hang on though, because if I had an exponent, if I had a constant number raised to another constant number, this c is not the same as this c. So I'd go back and I would subscript it all the way back out again. These were all the same c, but they were different than the one that I ended up with. Okay, so just a little review there, just kind of get us, try to push ourselves to do a little bit harder type of separation of variable. But that leads us into this next idea. What if, what if I decide to separate my variables over here? In other words, what if I get my y on this, on the side of dy, so I divide it by y again, and I move my dt to the other side. So k times y is that represents any proportional value. So it's directly proportional is what that k is. That's a direct proportional value. So we call that k value a proportional constant. At least we will here in a second. You'll see in this where we're going to go with this. And what ends up happening is we take the natural log of both sides. Whoop. That's supposed to be a dt right there. Sorry about that. So if I, and we're letting k be any constant number. So when I take the integral of that side, that's basically just k times that t value. And again, you guys don't necessarily need to know everything where I'm doing, but I do kind of want you to follow a little bit here because it's going to end up being something kind of cool. So if I swoop and solve it here, and again, I know that this value right here has to be a positive value. And since that has to be a positive value, friends, I know then that the absolute value y is going to be a positive value. So I can go ahead and just drop the absolute value because y is already going to be positive. So I get this y equals e times kt plus c. So if we do the kind of the same thing we just did before, I can break that up a little bit. And any constant number raised to a constant number is going to be a constant number. And again, those two constant numbers are not the same thing. So I'm going to go back and change that. But I end up with this weird little expression here where y equals c times e to the kt. And here's what that really represents. This is essentially what we call the exponential growth and decay model. So if I were to take that what we just found there is what we call the exponential growth and decay model. And what those things tell us is C is going to be the initial value. That's how much you start off with. K is your proportional constant, and T is just some period or time value. Now, friends, back when we dealt with compound interest, we had a continuous compounded interest. Back when you guys dealt with compound interest, you guys ended up dealing with an equation that was very similar to this. I don't know if you guys remember it or not. Y equals P times e to the RT, where P was the principal or the beginning amount. R was your interest rate, which is a constant number or a constant rate of proportion. So you've actually dealt with exponential growth and decay back when you guys dealt with compound interest, when it was compounded continuously. Now, what we find out with this exponential growth and decay model, anything that grows exponentially or decays exponentially will follow this model. And if the K value, if that proportion value is greater than 0, that proportion value is greater than 0, then it is exponential growth. If the proportion value is less than 0, then it is decay. And again, you don't have to worry about whether it is unless you're looking at an equation, because it'll, as we go through these, it'll just automatically kind of pop up. So we're going to use this exponential growth and decay model. So we use a little bit of integration to create it, but pretty much everything we're going to do for the remainder of this section is actually just algebra 2 or integrated 3. So, for instance, it says the rate of y is proportional to the value of x, or to the value of y. So all of a sudden, that tells me that I am dealing with my proportion equation, my growth and decay equation. And then what I have here is I essentially have a couple ordered pairs. T of 0 equals 3, and T of 3, oops, wrong color, and T of 3, y equals 18. So what we can do is we can use those numbers and plug them in. So when y is 3, t is 0. When y is 18, t is 3. And what we're going to end up doing here, friends, is we're really just solving a system of equations. So if I'm solving that system of equations, k times 0 is 0, so I get 3 equals c e to the 0. And anything to the 0 power is 1, so 3 equals c times 1. So 3 equals c. That's the initial value. And then I can plug it in to the c in my other equation to try to figure out what my k value is. So 6 equals e to the 3k. And I'm going to go ahead and swoop it here. So log base e of 6, so natural log of 6 equals 3k. And then we're going to divide by 3. So 1/3 times the natural log of 6 equals k. So now, if I go back to my original growth model here, y equals c times e to the kt, using those values, I can create a growth model that I can use to solve for any value. So I found out the initial value was 3. And then I found out my constant of proportion, my proportionality constant was 1/3 the natural log of 6. Times t. So from there, I could use that now to figure out any value I want. So if I want to know the value of y when t equals 7, all I'm really going to do is just plug in 7 for t. So 3e to the 1/3 natural log of 6 times 7. And so now we just go to our calculator, we're going to plug it in, and we'll create a value. Again, we use calculus to come up with this formula, but there really isn't any calculus involved here because we're just going to use algebra to solve it. So y is approximately 196.2490. So what our job to do then is to try to take this and use it in some sort of real life application setting. So some real type of application type setting where we can apply this knowledge to something else. So let's take a look at a problem here. Radium has a half-life of 1,599 years. 24 grams of the radium isotope was released from a storage container. How long will it take for the 24 grams to decay to 1 gram? So first you need to know what a half-life is. Half-life is basically how long it takes for something for you to get half of something. So we're going to use our equation here, y equals c e to the kt. And I'm going to plug in the values I know. So I started off with 24 grams. So when t equals 0, y is 24. And now I'm dealing with a half-life. So even though it doesn't directly say it, a half-life. So in this case, t isn't number years, it's the number of half-life periods. So after one half-life, I would have half of of the amount that I started off with. So if I start off with 24, half of that would be 12. So again, t isn't years here. T is going to be referring to the number of half-life periods. So how many half-lives are we going to be dealing with? So we plug in our numbers. 24 equals c e to the k times 0. And we plug in our other value, 12 equals c e to the k times 1. And if we solve this all the way down, friends, I end up with 24 equals c. So that's the beginning amount, which we already knew. Could have probably skipped it, but I like to just usually go through and prove it just to make sure I know what I'm doing here. So I can plug it into the other one here. And I'm going to go through and figure out what this half-life or this proportional value is going to be. So 12 over 24, that's 1/2, equals e to the k, and then natural log of 1/2 equals k. So that's my proportionality constant. So that means my whole equation then would be y equals my original value, my c value, and then e and my k value, and then my t. So another way to think of this here, so I can actually clean this one up. I don't know if you guys see that or not. Let's see. Let's see if I can actually figure out how to clean this one up here. Sometimes works out pretty nicely. I'm just going to rewrite that, put the t in front. And I learned, friends, that if I ever have a number or in front of my natural log, it can become an exponent. So we go back, we use our rules of logs, and I can move that t to the exponent of 1/2. The reason why that's kind of cool is, again, e and natural log, they're inverses of each other. So right here, where I have an e raised to the natural log, those are inverses of each other, so they would end up essentially just canceling each other out. So why? Sometimes it helps to kind of clean things up a little bit to create something that's a little bit easier to use. So 24 1/2 to the t. Now, I'm trying to figure out how long it took me to have 1 gram. So if I wanted 1 gram left, I'm going to plug 1 in for y, and I'm going to solve for t. So 1/24 equals 1/2 t. I'm going to natural log both sides. And I'm going to move that t in front of the natural log of 1/2. I'm going to divide by natural log of 1/2. So that'll tell me how many half-life periods took place to get from 24 grams down to 1 gram. Now, again, it didn't tell me what it was, it just told me that it happened. All right, tell me how many periods. So I don't know the exact time, I just know how many periods took place. So I get 4.584962,501. So just a little more than 4.5 half-lives took place. Now, friends, this is where we come back to the fact that we know how long a half-life is. So 1 half-life is 15,999 years. So what I'm going to do here is I want to figure out how many of these are. So essentially, I'm going to just go take my t value. So the number of half-lives is going to be equal to 1599 times t. So we end up with 1599 times that big ugly decimal. Which would be about 7,331 years. And it's calculus, so friends, we have to make sure that we always put it in context. It will take approximately 7,331 years for 24 grams of radium to decay to 1 gram. All right, well, we got one more to try here, and then we'll go ahead and call it a day, friends. One more to try. So let's just kind of scroll down here. You guys go ahead and pause the video and take a shot at this, see what you guys can do with it. All right, let's see how you did. First of all, I see law of exponential growth. So that tells me I'm going to be dealing with exponential growth. So y equals c times e to the kt. On this one, I'm told that the second day there were 800 mosquitoes. So in other words, when t is 2, y is 800. Then on the 5th day, I have 2,800 mosquitoes. So notice I didn't get the initial day. And that's kind of what they're asking me for here on the part A. So on t equals 5, y is 28. So what they're asking me for is how many mosquitoes did we start with? So in other words, what is y when t equals 0? Or another way to think of it is I'm asked for what's the c value? What's the c value in this equation? So let's take our values and let's set up 2 equations. So here on part A, (800) equals c e to the k times 2. And then we have the other equation, 2,800 equals c times e to the k times 5. We're doing part A here. So now, friends, I'll be honest. I have 5 k's here. So c e to the 5k. I believe I can break these up because I can break up multiplication anytime I want to with addition. So if I want to multiply things with the same base, I add their exponents. Well, I should then be able to go back and do the opposite. So I can e to the 2k times e to the 3k. They have the same base. So if I add their exponents, I get 5k. So I can separate them. And the reason I wanted to do that, friends, or I'm hoping that you guys did it as well, is I see over here c e to the 2k. I can take that 800 and plug it in for c times e to the 2k. Now, it didn't help me figure out what the initial value is yet, but it will allow me to go through and figure out what my constant value is going to be, my k value. So when I divide by 800 from both sides, friends, I end up with 3.5. So when I swing over there, I get natural log of 3.5 equals 3k. So 1/3 times the natural log of 3.5 is k. From there, I know what my k value is. I'm going to go ahead and plug that back in now. So y equals c times e to the whatever k was, 1/3 the natural log of 3.5. And multiplying the entire thing by t. So that's what I know so far. Well, friends, if we come back here, I now know what k is. I can come back and take my red equation there and figure out what the C value is. So we don't really need that blue one yet. We'll need that for the part B, because our answer to part A is going to literally be found just by plugging it into this equation right here. 1/3 the natural log of 3.5. So by plugging in my K value into that original red equation, my first one, when T equals 2, Y is 800, I can actually divide both sides by that to figure out what C is. So 2/3 the natural log of 3.5. That's going to be what C is going to be equal to. And friends, that when I plug it into my calculator, I get 347.0387. .396. Now I'd go ahead and store that value because we're going to need to use it again here in a second. And I don't want to necessarily be writing it over and over again. So really what we're saying here then is 347 is my approximate value for mosquitoes. There were approximately 347 mosquitoes when the experiment, always give it context. Okay, so we know our red value, we know our green value. Part B said, well, how many will there be? How many will there be on the 9th day? So if we go back to our original equation here now, B. So we started writing our equation. I now know the C value. I can plug that in here. And again, I'd probably write this if I was on the AP test. I'd leave this as C because I already defined what C was. I wouldn't keep rewriting it over and over and over again. But just so there's no confusion on the video, I'm going to go ahead and rewrite it. And then we have our E raised to So we've been kind of dealing with this, finding values here to make this thing cleaner. So what I want to do then is I want to figure out how many there are in the 9th day. All right, I can do that. So I'm going to plug 9 in for T. So I'm going to plug in 9 for T. And when we do that, we get that is going to be approximately 14,879.28596. In other words, after 9 days of performing the experiment, there was approximately 14,879.28596 879 mosquitoes. I round to the nearest number because I don't know about you friends, I've never seen a part of a mosquito before. That's called when the mosquito meets the fly swatter. So we want to make sure we keep that as a random, reasonable number. All right, so a little bit of calculus, but mostly algebra 2. All right, friends, good luck with it. We'll talk more about it tomorrow. Take care.